In the gradient parameters box, we have the separation of the two sensors, 1.5 meter. We have the magnetic sensor channel number 1. We list that as number 1. We have the magnetic sensor number 2 channel, which is channel 2. The gradient type will be pseudo-analytic signal. We could compute the horizontal gradient, or if we had a third sensor, we could compute the analytic signal, but we have found that the pseudo-analytic signal duplicates the final results of the third sensor analytic signal, and so therefore we can do with two sensors what three sensors, acquiring three sensors worth of data would provide. The vertical separation, we're computing that as 1.5 meters. So we're upward continuing the vertical gradient as though that third sensor were at 1.5 meters. We save into a data file. I'm saving it as demo grad.dat file. We want to load the data upon completion, so we check this box. And we want to remove the median prior to operation. By removing the median in the data, the analytic signal is a smoother representation and also tends to remove the geology and provide us just those anomalies which are of interest on smaller wavelengths. Okay, we click OK, and we are now computing the gradient. We're splitting the lines. 56 profiles were loaded. Okay, we've now loaded the analytic signal grid map, and we see that there is only one data per line. So we no longer have the dual lines, the dual data files per line, but in fact now we have computed the analytic signal, which is represented as a single traverse. Again, we can go to New and open the profile view so that we can see the individual profiles. I'll expand the box. We can see right away that the data is higher frequency, that some of the geology has been removed. We can go to File and open the browser so that we can look through individual analytic signal profiles. We can see that there are higher frequency components, and we can see that the majority of the anomalies are very high frequency, meaning that they are actually objects on the seafloor. Okay, when we have gone through the 56 lines, and we can see that as we select line by line, it's showing us on the gridded profile map where these lines are located. We select one by one and go through and make sure that we don't have anything that's completely out of range or anomalous beyond the realms of the other data files, the other data profiles. Okay. Now we're able to build and actually do the contouring of this data file. So we select Profiles, Interpolate Grid, and we'll use a spline grid. We're going to select the intervals at approximately half a meter. 1 meter or half meter, I'm going to change these to 1 meter. The gridding, of course, is done on a X and Y coordinate surface, and so to grid it, even though we're sampling more than 1 meter, faster along the line than 1 meter, 1 meter in the X and Y direction is sufficient for this gridding. The tension is set at 0.25. This is how tight the contour will fit the data. Low constrained, we can constrain it by the minimum data. High constraint can be the maximum data. The format is NetCDF. This is a form of gridded data that is industry standard. Iterations we set at 2500. We set the convergence limit to 0. This actually allows the program to select its own limitations in the algorithm doing the interpolation. So when we set it to 0, it means that if the fit between the gridded data, the gridded value, and the actual data is not improving, then the algorithm, the procedure stops. So we set that to 0. Channels, we can set that to 1. There's only one channel here. And then we recommend that you click this filter data, which is using median value. The median value, again, allows the analytic signal to remove the geology and also to present the data in the best possible manner. We're going to output the file as I'm going to select data grids.nc and we'll select OK. And now it's doing the iterations. You'll see that the discrepancy between the data and the grid is now down to 0.02. It's done 700 iterations. Of course, the speed with which it does this process is based on the speed of the computer. This particular computer is an i7 processor. Okay, it says actual bitmap image is 2116 by 2864 pixels. This can slow down on the PC. Yes, to continue with this resolution, no to automatically reduce the cell screen size. And I'm just going to click yes here. As we can see, the map now shows each individual anomaly individually presented in a color coding. By the way, we can change the amount of palette, the type of palette we use. The palette type is uniform, and we've selected palette number 22, which is often used for analytic signal. The reason why is because the low end of it is white, and remember that we have actually made the map with median removal, which means that all of the anomalies are positive and that the minimum value is 0. So if we set the palette from 0 values and up, then we get just the analytic signal contour map, and the base map is white in the bottom. We can also put the actual profiles on or off the data set here. Again, see, now we've removed the profiles, or again we go to options, settings, and we can put the profiles on there. We can even show the stacked profiles if we want to on these individual contour lines. Again, options, settings, we can show profiles. By the way, to get these profile menu boxes to pick up, you unclick it, then re-click it, and the profile name of the profile dialog box will come up. Unclick the plot stack profiles, and now we can see the individual profiles and the contour lines from the analytic signal map. This can be printed out on a color printer, and there are additional surrounds information that we can put on, text, north arrow, and so forth. So, this is a brief introduction into generating an analytic signal map using MagPick. There are many procedures and processes here that we haven't gone into, but we wanted to give you an introduction to give you an idea of the power of the program. We would welcome any questions. Please send an email to sales@geometrics.com, and we'll make sure they're answered promptly. Thank you.